Now we're going to take a look at dependent events. So two events are dependent if knowing the outcome of the first event does provide information about the outcome of the second event. Dependent events can also be referred to as conditional probability. Just like with independent events, when we're looking at dependent events, we are not looking at the probability related to a single trial. We are looking at the results for more than one trial of an experiment. So we're looking at actions that are repeated more than once, typically. So we're going to start by looking at a contingency table, and we're going to find some conditional probabilities using a table. So for the first one, we're going to find the probability that a randomly selected person wants to have pizza rolls given they want to play poker. So this word here, given, when we're looking at a contingency table, is really our big key word, that this is a conditional probability. And this is the word that is going to tell us that the calculation we're going to do is going to be different than any other calculation we've previously done with a contingency table. So the way I'm going to write this out is I'm going to say that I want to find the probability that they want pizza rolls, and then I'm going to use a straight line to indicate given, and then I'm going to say poker. So what I'm going to look for is my numerator is going to be the probability, or the number rather, of people that wanted pizza rolls and poker. So the top piece is going to be the overlap of pizza rolls and poker. And then the bottom is going to be the total of whatever I have been given. So given they wanted to play poker. So the bottom is going to be the total number of people that wanted to play poker. So this is saying, given I've already narrowed this down to poker. We're gonna play poker. What is the probability that they also want pizza rolls? So the number of people that want pizza rolls and poker, we can see in our chart here, is 10. And then we divide that not by the overall total anymore, but now just by the total that want to play poker. So that's 10 over 25. So 10 over 25 gives us 0.4 for this probability. So if we continue on, the next one, find the probability that a randomly selected person wants to play Wii Bowling, given that they want cookies. So take a second and see if you can work that out. Pause the video, and then I will go ahead and go over the answer in just 1 second. All right, hopefully you pause the video and we can go over what the answer should be. So we're looking for the probability of Wii Bowling given that they want cookies. So again, the top should be the number of people that wanted Wii and cookies. And then we're going to divide that by the total number of what we were given. And we were given that they want cookies. So we've already said we're going to do cookies for the snack. So the total number of cookies. So if we look at our overlap of Wii Bowling and cookies, there were 4 people that wanted Wii Bowling and cookies. And then the total number of people that wanted cookies was 32. So 4 divided by 32 is 0.125. The next one is very similar, but a little bit different. Given that they want to play Wii Bowling, find the probability that a randomly selected person wants cookies. So now this one is starting with, given they want to play Wii Bowling, find the probability that a randomly selected person wants cookies. This one looks similar, but it is not the same. So probability that a person wants cookies given that they want to play Wii. Whatever comes after given is what goes after the line. That is what we've been given. So we're going to look again at the numbers that are in the overlap of cookies and Wii. But now we've been given the people that want to play Wii Bowling. So our denominator is going to be the total number of Wii. So our numerator is 4 again, but this time it's out of the 21 that want to play Wii Bowling. So that is 0.1905. And then the last example I have with this table says, if a person wants to play Monopoly, what is the probability that they want chips and dip? So this one doesn't have the word given. However, it does lead with if a person wants to play Monopoly. And that is our given statement. We're starting with the assumption that a person wants to play Monopoly. What is the probability that they want chips and dip? So for this one, what color have I haven't used green. There we go. Okay. So the probability of chips and dip given it is a person that wants to play Monopoly. So we want the number of chips and dip and Monopoly divided by the total number of Monopoly. So coming back up here, chips and dip and Monopoly had 17, and Monopoly itself had 40. So 17 out of 40. 40 people wanted to play Monopoly, and from those 40 that wanted to play Monopoly, 17 of them wanted chips and dip. So this is how we find conditional probability from a contingency table. We also can find dependent probability with multiplication. So in this example, you are reaching into your wallet from your for some change. You know that you have 3 quarters, 4 dimes, 6 nickels, and 9 pennies. Let's highlight those. 3 quarters, 4 dimes. I was going to change colors. It didn't change. 4 dimes, 6 nickels, and 9 pennies. If you do not put the coin back into your wallet after each pick, what is the probability that you grab a quarter, then a nickel, and then a penny? So this is the big key to this problem. If you do not put the coin back, this means you are doing something called sampling without replacement. And that makes this a dependent probability because the coin that I pull out the first time is going to affect what is left in my wallet for what I could grab on the next draw, the next coin I grab. So because I'm not replacing the coin after each time I grab a coin, this is a dependent probability. I'm affecting the outcome. I'm affecting the probability with each coin draw. So I want the probability that I grab a quarter followed by a nickel and then finally a penny. So probability of a quarter and a nickel and a penny. So first, I need to figure out how many coins I have in my wallet total. 6 plus 4 plus 6 plus 9, not 6, 3. This first one should be 3. 3 plus 4 plus 6 plus 9 is 22 coins. There are 22 coins in my wallet. So when I reach in and grab the first coin, the probability that that first coin is a quarter is 3 out of 22. Then I go in and I grab again. So I'm doing multiple coin grabs. So I'm going to multiply the probabilities. And now I want to get a nickel. So there are 6 nickels in my wallet, but I kept the quarter. So now there are only 21 coins left. And I'm going to reach in one more time. And I'm going to try and get a penny. I need 31 cents. There are 9 pennies, and now there are only 20 coins left. 3 times 6 times 9 is 162. 22 times 21 times 20 is 9,240. 162 divided by 9,240 is 0.0175. So less than a 2% probability that I'm able to reach into my wallet with these coins in there and I'm able to pull out a quarter and then a nickel and then a penny. And that sounds about right, because I don't know about you, but when I'm looking for the change that I need, I am never able to find the coins that I'm looking for. Maybe that's just me. But there you have it. Dependent events, conditional probability with a table and conditional probability with multiple repetitions of an action.